Today I'm here to talk about also the basis of Kubernetes, so I'm glad that Richie explained most of it, so I can skip some parts. I'm actually working at IBM, working on the managed Kubernetes and OpenShift service, which is a pretty interesting topic. I mean, why to talk about Kubernetes after it is 10 years old? It is the boring standard way of deploying containers, but things can get very tricky once it is broken. So like what to do when all of your nodes are not ready? You can still reach the API server but nothing else. Or like what if your cluster is working well, just logs and exec stopped working? You just changed some firewall rules, it shouldn't break that part, right? So I hope we can get closer to answer these questions today. Disclaimer might be familiar. So the content is based on implementation choices made at IBM, but contains several simplifications and changes for the better understanding. So colleagues in the audience might spot some of those. All right. Big numbers. IBM Cloud Kubernetes and OpenShift service. It started in mid 2017 with the managed Kubernetes service. We launched it also on bare metals, and in 2019 we have OpenShift as a service as well. The service is available worldwide in all the IBM-owned data centers, and also available on third-party infrastructures like in other clouds or on your on-prem system. The amount of clusters we manage is averaging about 10,000 instances, but sometimes it peaks at 25K, so we have a lot of short-lived clusters. And sometimes we manage almost 500,000 nodes in these clusters. We have automated patch updates and single-click minor release upgrades for the users. Agenda. What are managed services, managed cloud services, just very quickly? Why Kubernetes as a service is a tricky one compared to others. Some spoiler there. And we will jump into the design of a generic managed Kubernetes as a service. I will highlight some key ideas behind how to really make it managed. Yes. Okay, in a nutshell, what you can expect you get with the managed cloud service. Of course, you get some agreement, some service level agreement that it will work with some availability, and you can blame your provider if it doesn't. On the functionality side, it is usually automated resource lifecycle management on your behalf as a user with your limited access and control. And that's not a con, it is actually a benefit. So you don't have to take care about all the details. You have an opinionated set of defaults, and it should work in the environment you chose. Compliance, you also get compliance for what your provider is running for you. In some of the industries, it is the key. So most of our maintenance work in these services are really fighting with CVs and keep everything up to date. Some managed cloud services are simple from the user point of view. So if you get a database as a service or a message queue or something, it is usually like you get your API endpoint, either you get or set your credentials, and you are good to go. You just need to make that endpoint available from your environment. With Kubernetes, however, it is a composition of a lot of cloud resources, and you need to take care a lot, actually, even if you consume it through a managed service. But let's say we have Kubernetes at home, like on-prem or wherever you want it. This is a basic stack. You have your own data center, you have your facilities incoming, floor space, redundant power, network, whatever. Then you realize some network layer on top. You have your site router, your switches, you enable DNS and DHCP, whatever. You put some storage either besides or on top of your network resources, and then you add compute, either physical or virtual. On the compute, you have your operating system, and finally, on top of your computes, you install Kubernetes as cluster management. You install the core with your tool chain of your choice, like kubeadmin, and then you will instantly add some core services like in-cluster DNS, network plugin, you enable your storage solution that you created below, and you are good to go to deploy your applications. You can move into the cloud, into an IaaS stack. Then you pay for up to the compute, and you expect that it will work, and you still install Kubernetes on top yourself. You can do it also with basic tooling from the community, or in case of OpenShift, for example, this is what you have if you choose to install OpenShift on your own. So from the cloud provider point of view, this will not be a Kubernetes or an OpenShift cluster. It is just a bunch of resources, virtual machines, network resources, subnets, gateways, whatever. It is only a Kubernetes cluster in your view. You manage it still. Or you can go fully managed. You have everything from your provider, and you are expected to only run your application on top. And this is what we will achieve today here. Managed services are cooler when you have them available globally. So if you have multiple data centers, you can get your service instances closer to their need. Sometimes it is mandatory to run or store the end user data locally in their country. It is very important for some industries. With publicly available clouds, you get some nice global API, unified web console, unified billing, and that's where we need to fit our Kubernetes as a service. Okay, that was the high-level view. Let's look inside. On the right, you can see a brand new single node kubeadmin cluster initiated. These are all the pods which are running in the system. On the left, you get the managed pod list. This example is from IBM Managed Kubernetes Service. What we have here, let's see what we have in common. Calico, if you are not familiar with that, is one of the most popular open and free CNI plugins. It has multiple components. It has its own API server to deal with the Calico-specific CRDs. It has its own controllers to handle node events. It has its node agent. This is the point of running a CNI. If we would have multiple nodes in the cluster, we would have more Calico nodes. It is a daemon set. It is really the one who is plumbing together pod networks. We also have Calico Taifa, which is basically an API proxy for scalability. And at the bottom, so Tigera is the company who produces Calico. They create their own operators to manage everything which is related to Calico. All right, this is common. We also have core DNS on both sides. This is the in-cluster service for providing DNS. So it will resolve either in-cluster services or external public DNS names using the upstream resolvers. Let's remove that as well. And what we have now is really truly different. On the right-hand side, you should see everything that Richie explained already. So we have the etcd and the three core components of the Kubernetes control plane. However, on the left side, it is totally missing. We have some strange named proxy-like pods running there. Okay. Let's start with the self-hosted version and slowly convert it to a managed idea. So we have everything here from the right-hand side of the previous slide. On the left, I collected all the components which are totally independent of your cluster nodes. Like etcd is just a data store. It doesn't. It is not important where it is running. Our API server is just a stateless API server operating on top of etcd, and then we have our controllers and scheduler. On the right-hand side, we have our applications. Of course, we have kubelet, which handles the management of all applications and pods. And then we have the node agents like the Calico node itself, or maybe some storage integration, special hardware integration to your nodes. So on the right-hand side, we have everything which must run on the nodes. In between the two, we have the thing called service endpoint, which in the self-hosted case is just an in-cluster service in your default namespace, right? So that's the network endpoint where you can access your API. If you check the arrows, everything is pointing towards the service endpoint, and API server is the single one which is reaching it, which is receiving it, sorry. Okay, let's split this into two halves. So on the left side, we have the control plane, which are not bound to the nodes. And on the right-hand side, we have the actual workload and the extra pods which must run on the nodes locally. Okay, I removed some of the arrows, and now I'm adding the two proxies that we saw on the left-hand side on the pod list. So master proxy is usually just a dump TCP forward proxy. You can do it with HA proxy, Nginx, whatever. It will be the single entity in your cluster which knows where your service endpoint is. And then if you change your Kubernetes in-cluster service to some static IP where this master proxy is listening on all the nodes, then you can divert the traffic and have every entity, including kubelet itself, when they want to reach out to the API, they will talk to the master proxy first. Okay, what's connectivity for? There are tricky cases when you fetch logs, do kubectl exec, kubectl copy, or you have webhooks serving in your cluster. In these cases, the API server must do an outbound on-demand connection back to your cluster. And this is a problem if you want to remove your control plane from your cluster, because your security team wouldn't like if you want to open up TCP ports on every node in this connectivity service to allow in any strangers. So instead, connectivity has a server part where connectivity agents on all of the nodes can connect back first, creating a permanent gRPC tunnel. And so you can configure your API server to talk to connectivity if it wants to reach back to the cluster. Connectivity is a part of the open source community, Kubernetes community projects. It is well integrated with the API server. So that's the trick we need. And now we have all the arrows, like TCP connections, are outbound from your worker nodes. Okay, how the service endpoint looks like in this case. We still have the in-cluster service called Kubernetes in the default namespace. It is a mandatory thing. You must have it. The only change is that it points to our master proxy. Okay, for external access and for the master proxy itself, the true location of the API server must be registered somewhere which is resolvable on your worker nodes. So you can register it wherever you like to be able to resolve it from the nodes themselves. For truly external kubectl clients, you can expose it to the public if you like, and so you can control both public and private as you like. Okay, connectivity. As connectivity agents are connecting to their own server and not the API server, you must have some other distinct endpoint to expose connectivity. In a cloud environment, this service endpoint is usually a first-class citizen. In a VPC environment, you are usually able to create such gateways which are routing your traffic to a remote location. Okay. And then we are done. On your nodes, all what is running is really your workload, some mandatory node agents, and some proxies. Why this is useful? So for the control plane, if the user cannot access it, user cannot break it. You have to hand out administrative kube configs to all of your users. It is good if you limit. The point is that your control plane is truly outside of your cluster now, so it is not hidden with some magic code. It is really running outside. And so the provider can lifecycle manage, monitor, scale, update, whatever they want to do with the control plane itself. And of course, data plane is the trickier part. So the work node responsibility is usually shared as you give administrative privileges to your users. As you could see in the other room, they can run privileged pods, they can escape, and they really own the nodes, or at least you should treat it like that. Still, the provider must lifecycle manage some cluster components like the node agents for compatibility and compliance. Okay, how to scale, especially the control plane. I zoomed out a bit compared to the last chart. So on the left, you have your master components. They are behind the service endpoint. And then you have your nodes where the real workload is running. The nodes are in the customer account. Say we are in a VPC environment. They have their isolated VPC and their subnets. The nodes are running there. And you have some endpoint gateways towards the service endpoint. Now, of course, it is running in a single multi-zone data center. So if the masters are just pods, as we could see, API server scheduler, controller manager, or etc itself, if they are just pods, do we need master nodes? Or if they are just regular pods, couldn't they run in another cluster maybe? And if they can, you can isolate them in their own namespace probably. And the most important thing, you can run multiple of them. So you can run multiple masters in the same cluster, and this is very important. This cluster is not the customer's cluster. It is a totally different cluster running in another account which is owned by the provider itself. And yeah, once you have your masters collected in a single place, you can manage them. There is no firewall, no whatever, which may block the operation of the provider if you want to manage them. You can run your management services like lifecycle management, related jobs, health monitoring, whatever. They can access these masters. Such a control plane cluster is good up to like 500, hosting 500 masters. What happens if we run out of this capacity? We can do it once more. You can keep creating these huge clusters, and you can host more and more masters. Again, each of them can belong to different customers and different clusters at the end. Okay, what to do with the management clusters themselves? So could they be just very similar clusters as the end user cluster? Yes, they can. So you can reiterate on this trick and run the control plane clusters master again in some other clusters, and then you have very seamless lifecycle management. Actually, you use your own automations just like the user use it. You cannot do this infinitely, so you can put this together in arbitrary hierarchies. But at the end, if you want to keep like the blast radius of any event located, you cannot really host elsewhere any parts, which means there is a single cluster in every data center, which must be more or less self-hosted. So the cluster on the left-hand side does not enjoy all the automated lifecycle management as all the others. So yeah, this is the price of it. Okay, just to recap a bit, there is no embedded virtualization or no any trick. It is just really pods running in different clusters. Some clusters are yours, some are not, and that's the idea. Okay, how to integrate it? Of course, managed services are running in layers, so you most probably want to enjoy nice integration with the underlying infrastructure. So back to the original picture, what happens if you want to expose your application, or what happens if you want to create persistent storage? Those are usually purchased from the underlying infrastructure as a service. There is a component we didn't talk about, which is the Cloud Controller Manager. It is a standard component in the Kubernetes architecture, but it is vendor specific. So the community gives you an SDK or a framework. It is very similar to an operator where you can install or you can write your own hooks, and they can react to node creation, load balancer service creation, and a few other things. It is a pure API client, and at its back, it can do basically whatever you want. It usually owns a copy of your API key, so it can really act on your behalf towards the infrastructure. Say the user created a load balancer service, which does not do anything on its own. It should be picked up by this controller manager, and then, of course, it is totally infrastructure dependent, so it depends on where you are, but the implementation is usually talking on your behalf to the infrastructure. Please create a load balancer instance in that VPC where the backends are the nodes of your cluster. Same goes if you provision some persistent volume claims. Probably you have your storage controller embedded into the Cloud Controller Manager, or you run it, you get it as a separate pod or deployment. It will react to your ask to create a file share or a block device or whatever you need to mount in your application pods. Okay, there are cases when you cannot express your wish to the cluster API itself. For example, when you want to create the cluster itself or you want to scale the cluster, you cannot directly do it with the cluster API. So there must be some higher level API as you talk to, and this is the Kubernetes as a Service API itself. This is what you use to create the cluster, to upgrade it, or do anything on the higher level. So in case you like to create a new worker pool or just scale the existing one, you usually talk to this Kubernetes as a Service API, and again, on your behalf, it will ask the IS to provision those nodes, and then you scale your cluster. So this is the other idea, how it becomes managed. And so far I talked about Kubernetes, but OpenShift is really similar. At its core, it is also Kubernetes. And yeah, some words about manage OpenShift. I'm not aware of any open projects that helps you create managed control planes or just control planes of Kubernetes. But in case of OpenShift, you have this tool chain. It is called Hypershift. So of course it is provided by Red Hat. It is a bunch of operators. And yeah, this is the original slide. As you can see, it is very similar that I just explained. You have your special cluster to host control planes. There you express your intention to create clusters in the form of CRDs. It will reconcile and it will create the masters for you, and then you can join your workers. All right. Recap. With managed services, you trust your provider. They will do better than you. You cannot tweak all the dirty details. You have an opinionated set of settings, but it should still work. It is not really magic. It is again just someone else's computer or someone else's cluster in this case. There is no proprietary secret sauce in the cluster. It is not custom compiled Kubernetes code at all. It is really the same as you run in the self-hosted case. All the proprietary code is usually in the support and management functions, in the APIs you use on a higher level, and of course in the operations. And that was my last slide. Thank you.
All right.